Good morning, colleagues. Uh, I have to quickly do some video to explain the slides. Your input are highly welcome. So the purpose of this slide is that the objective is to add and subtract algebraic fraction. That is not even the main objective of partial fraction under this, but we shall use that to delve into the explanation of partial fraction. And that's the second objective, explain partial fraction. Then the second one, now we'll look at the decomposition of fractions, partial fractions under the following categories: type 1, type 2, type 3, and type 4. Okay, quickly. There's a question, a problem. These two algebraic fractions are to be added. Let's look at how it is performed. 2 over x minus 1 plus 1 over x minus 2. Ideally, we always look for the LCM. So the LCM is x minus 1, x minus 2. So this will take care of this. The 2 will multiply x minus 2. Then this also take care of this. Then the 1 will multiply this bracket and to be the same value, x minus 1. Opening bracket, we have 2x minus 4 plus x minus 1 all over x minus 1, x minus 2. Good. Simplifying the numerator, we're going to have 3x minus 5, that is 2x plus x, and the minus 4 minus 1 over x minus 1, x minus 2. So that's what we have here in the slide. 3x minus 5 on x minus 1, x minus 2. Then we'll go to the next slide, the partial fraction itself. So from the previous exercise, you know that when we add this fraction to this fraction, we get it. So partial fractions are the fractions used for the decomposition of rational expressions. When an expression, an algebraic expression is split into a sum of two or more rational expressions, then each part is called a partial fraction. Hence, basically, it is the reverse of addition or subtraction of rational expressions. What it just means is that we have been given these two in the previous exercise, these two fractions to add, and it yielded this. When you are also given the right hand side and asked to break it down to each constituent fraction, eh, that is what we call resolving or decomposition into partial fractions. So when you are changing this back to this one, eh, then you are resolving or you are breaking it down into partial fractions. Each fraction here is a part of this one. So this is a partial fraction, this is a partial fraction, all comes together to make the whole of this. So as I wrote here, consequently, we can be given this expression, 3x minus 5 over x minus 1, x minus 2, and be asked to decompose it into its constituent partial fractions. Sorry, so the two words. Its constituent partial fractions. Okay, now let's go. Decomposition of partial fraction itself. When we are decomposing partial fractions, the type, when the question is given, you must diagnose the type of partial fraction it is before you can handle it. The type will determine the process that needs to be followed to decompose the fraction. So here we are looking at type 1, when the fraction is having a linear factor as a denominator, a linear factor. When we talk about linear factor, we are talking about a, a factor that has is in the form of ax plus b, like the equation of a straight line, linear factor. The highest power of x supposed to be 1. That is called a linear factor. A linear factor. A linear factor. Okay, so how do we make decompose a linear factor? Always, when the question is posed, you must first look at the problem. whether it's a proper fraction. That is the first thing. You must first check whether it's a proper fraction. Eh? To check whether it's a proper fraction, we just look at the denominator and the numerator, the degree of the denominator and the numerator. For example, if I have x squared plus 3x minus 2 all on x plus 1, this is an improper fraction. This is an improper fraction because the power here is 2 and the highest power here is 1. So we say the degree of the numerator is 2. The degree of the numerator is 2, whereas the degree of the denominator is 1. So it becomes an improper fraction. Another example, if I have x squared over x minus 1, x plus 1, this is also an improper fraction because we know that the degree of the numerator is 2. And when this one is expanded into a quadratic expression, we're going to get x squared minus 1, x squared minus 1, and the degree is 2. In a proper fraction, the degree of the denominator should be bigger than the degree of the numerator. They shouldn't be equal. The degree of the denominator should always be higher than the degree of the numerator. Good. So let's look at the first question. We are being asked to resolve this into partial fractions. The question is 3x minus 5, x minus 1 on x minus 1, x minus 2. In fact, this is the previous question that we added. If you come back here, the one we added, we got this. I have just brought that one to see whether we can decompose it back. We can decompose it back to get our uh, uh, partial fractions back. So let's go and look at how this will be done. Let's look at how this will be done. Let me clear the screen. Okay. Okay, now let's go on. So let's pick the question. So the question is, sorry, 3x minus 5 on x minus 1, x minus 2, x minus 2. For every linear denominator, when you are resolving it into partial fraction, this factor will stand alone, this factor will stand alone. So we'll have x minus 1, and then this one will be x minus 2 to stand alone as separate denominators. But they will pick constant numerators. Their numerators will be constant. The reason is that they are linear factors. So we can donate that constant denominator of a letter A here, a constant number denominator of a letter A here, and that one with a letter B here. Now we'll add them together. Now, at this point, we do the normal addition we did in the previous exercise. So the LCM will be x minus 1, x minus 2. So here, the A will multiply s minus 2, the A will multiply s minus 2, and then the B will multiply s minus 1. And this is identical to 3x minus 5 on s minus 1, s minus 2. Good. Good. Let's proceed. Since the numerators are the same, we can equate numerators. We can say 3x minus 5 is identical to a s minus 2 plus b s minus 1. We are using the identical symbol here because of this type of equation. It is true for every value of x. The left hand side and the right hand side is true for every value of x that we take. So there are two methods. After here, now we look for the values of a and b. A and b. There are two methods to do that. We have one, the cover up rule, and then two, expanding and comparing coefficients. So let's try the cover up rule. Cover up rule. Cover up rule, you pick um, a value of x such that one of the variable would drop. That is why we call it cover up rule. So for example, if I assume that x is equal to 2, here becomes 0, a drops, then I solve for my b, cover up rule. We aim at dropping one of the variables by predicting an x value that will drop one of the constant a or b. So when x is equal to 2, when x is equal to 2, when x is equal to 2, the whole thing here breaks down. And here will be 2 minus 1, and here is 2 minus 5. 3 into 2 minus 5. The answer here will be 1, and then here also will be 1. So we'll get b is equal to 1. Then we also predict another value that will drop the b so that we can solve a. So let's pick another value. So let's say when x is equal to 1, this will let the b drop. When x is equal to 1, this becomes 0. The b drop breaks down. So we'll have x is equal to 1. So 1 minus 2 here, multiplying the a. 1 minus 2 here, multiplying the a. And the left hand side with 3 times 1 minus 5. 3 times 1 minus 5. So the computation here will give us negative 2. Negative 2. And here we'll get negative 1. So negative 2 will equal to negative a, which will imply our a is equal to positive 2. So bringing their values back into their position. And so a is 2. And then the b we had 1. What is b? I wrote to green pen. Okay, I wrote it somewhere. So the b is also 1. Bringing it to their constituent position, you will see that we will get the values of our original fractions back. Let's go back. So you can see that the a is 2 and the b is 1. So that is how partial fractions are resolved in type 1. Let's go if there's let's check whether there's another example. So that's the cover up proof. So let's look at the expansion and comparing coefficients. In that instant, you expand and compare coefficients. So 3x minus 5, we expand, we open the bracket. And we are doing it here. We open the bracket here. A times x is what? Ax. Then a times negative 2 is negative 2a plus bx, this times this, minus b. So 3x minus 5 is equal to ax plus bx minus 2a minus b. Here I'm just trying to group like this. Then 3x minus 5, then we factorize the x out, a plus b x, then minus 2a minus b. Then we compare or comparing. A plus b is equal to 3. That's comparing coefficient of x. So here, the coefficient of x on the left hand side is 3. The coefficient of x of the right hand side is a plus b. So we can say they are equal. Then these are constant terms without a variable x. So we can say minus 2a minus b is equal to the constant term on the left. So minus 5 is equal to minus 2a minus b. Then solve these two equations simultaneously. You come and arrive at a is equal to 2 and a is equal to 1. You will come and put them back into their respective positions over, what is it? Their respective position over here. Good. Just see whether there's another example. Now, express this in partial fraction. This is a proper fraction. So proceed to factorize the denominator. Always, you must try as much as possible to factorize the denominator to get the factors within the denominator. When it's a quadratic expression and it cannot be factorized, it is treated as another type, partial fraction with a quadratic denominator. But you don't just see it's a quadratic denominator when the thing can be factorized. For example, this is a quadratic expression. 1 minus x squared is a quadratic expression. But we don't treat it as a type with a quadratic denominator when we know that it can be factorized. If it can be factorized, you factorize it to get a linear factor. Then it falls under the first type, type 1, with linear factors. So let's check the degree. Here the degree is 2, and then numerator the degree is 1. So this is a proper fraction. So we'll factorize the denominator. So when we factorize the denominator, this is a difference of 2 squares. So this is 1 minus x, 1 plus x. Since the denominators are linear factors, each of them will have a numerator which is constant, a and b. So we have 5 minus 3x over 1 minus x, 1 plus x. We identical to a over 1 minus x plus b over 1 plus x. Then we express the right hand side as a single fraction. So expressing it as a single fraction, we know already the LCM is 1 minus x, 1 plus x. So here this will take care of this, and the 1 plus x will multiply the a. And then this one will take care of this, and then the 1 minus x will also multiply the b. This implies 5 minus 2x is equal to a 1 plus x, 1 plus b, 1 minus x. What we just did here is just to equate the numerator. Choosing x is equal to 1. That's cover up to. You can also expand and compare coefficients, as I said in the previous example. So choosing x is equal to 1. What I'm trying to do, I want to make one of the variable drop. One of the variable, either a or b, drop. So when x is equal to 1, we just substitute in. It will be 5 minus 2 times 1 equal a into bracket 1 plus 1 plus b 1 minus 1. So the b will drop. So we have 3 is equal to 3, 2a. Then a is equal to what? 3 over 2. And when x is equal to negative 1, the a drops. And when you solve, blah, 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 you get 7 over 2. Then you put them back into their constituent positions. Let's see another example. The denominator is a quadratic denominator, but it's not treated as type 1, the type with a quadratic denominator, because it can be factorized. Now, this one to the degree of the denominator is higher than the degree of the numerator. So this is a proper fraction. When it is an improper fraction, there's another method of handling that. So since this is a proper fraction, we proceed to factorize the denominator. And factorizing the denominator, we have x plus 1, 2x plus 1, x minus 1. And since they are all linear factors, they are going to have a constant as their numerator. So we represent that with a and b. So that is that. Then we clear the numerator by multiplying to the numerator on the left side and on both sides. This one clearing fraction is the same thing. So when you clear, you have 3x is equal to a x minus 1 plus b 2x plus 1. We combine like term, that is, we expand and compare what do you call it, coefficients. So when you open this, we have ax minus a, then 2bx plus b. Then we group like terms, and then you factorize the x out. The constant term will be a minus a plus b. Then comparing coefficients, a plus 2b is the coefficient of x here. So that should be equal to 3, the coefficient of x here. The constant term, a plus b, there's no constant term here. So a plus b will equal to 0. Then we solve it simultaneously, and then you see that a is equal to 1 and b is equal to 1. Then you put that back. Okay. So this is an example you need to try. Then go on to the denominator of repeated factor. A denominator with repeated factor. For any denominator with a repeated factor, such as a plus x raised to the power n, there will be fractions such as a plus x plus a plus x squared plus a plus x cubed, that up to d plus x plus um, raised to the power n. I think let me explain that one clearly. What it means is that if I have a denominator which is x plus 1 raised to the power 2, eh, we are going to have a over x plus 1, then plus b over x plus 1 squared. If the denominator is x plus 1 cube, I am going to have a plus x plus 1 plus b plus x plus 1 squared plus b plus x plus 1 cube. If I have a numerator which is x plus 1 raised to the power 4, it's going to have a over x plus 1, then plus b over x plus 1 all squared plus c, here should have been c, sorry. So c plus 1 over x all cubed, then plus d over x plus 1 raised to the power 4, sorry, etc., etc. So if I have another denominator, let's say x plus 1 raised to the power 5, then I will have a over x plus 1 plus b over x plus 1 raised to the power 2 plus c over x plus 1 cube r2. So I get the denominator x plus 1 raised to the power 5, x plus 1. So I get a denominator x plus 1 raised to the power 5, x plus 1 power 5. Okay, that is why in the slide we said x plus 1 power n, you will do it 1 over a over s plus 1. No, let me write what's actually in the slide. I'm coming. In the slide, we have over x plus a plus x power n. So we are going to have capital A plus x plus a plus x with the power 2, and plus a c, this is supposed to be b, over a plus x to the power 3 r2 until we get what? X plus a plus x power n. So take note of that. Okay, so let's look at this question. So this one is a repeated factor. It has already been factorized. If we expand the bracket, we are going to get the degree of the denominator of 2, and that of the numerator is 1. So that will give us a proper fraction. So we can proceed. Mhm. So the denominator here will give us a x minus 2, then b x minus 2 all squared. So we combined the right hand side, expressing the right hand side as inverse fraction. The LCM is x minus 2 all squared, and this is how it becomes. Then we equate the numerator 5 minus 3x is equal to this. Then choosing x is equal to 2, cover up to the a will drop, and we have negative 1 is equal to b, or b is equal to negative 1. Then we choose any value for x because we can't drop the b, and substitute. We can't drop substitute. We're supposed to substitute a. Because no. Okay, substitute b. Very good. We can't drop the b. It's correct. It's in order. Substitute b. Well, we know the value of b here. So choose any value for x and substitute b. So when x is equal to 5, we have 5 minus 3 times 3 is equal to a 3 minus 2, then minus 1 because the b is 1. Then solving for that, we'll have a is equal to negative 3. Then we come and put it back in their respective position at the top here. on to the next one. In this question, we have a linear factor and a repeated factor. A linear factor and a repeated factor. So the denominator of the linear factor will be this, a over s minus 1. But for the repeated factor, it will have two components. So b over s minus plus 2, c over s plus 2. Likewise, we find the LCM and combine them together. Then we equate the numerator. So then using the cover up rule, when s is equal to negative 2, you slot inside your c with 42. When x is equal to negative 2, a will drop, b will drop because here will turn 0 and it will affect the whole of this expression. So our c will be equal to negative 2. And when s is equal to 1, and when s is equal to 1, b will drop, c also drop. Then we solve for a. Then we choose when s is equal to 0, any other number. We just put it inside. Then blah 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 blah. Solving further, we'll get the value of our a and b. Then we'll a, b, and c. Then we'll bring them back to. So these are further questions. Thank you very much. I will try and see what I can do the quadratic denominator and the what do you call it, the improper fraction before 7 o'clock.